Welcome back, traveler. Tonight we explore something we were never supposed to find this way. Before we go any further, if you enjoy calm, late-night journeys through strange corners of space, take a second to like the video, subscribe to the channel, and leave a comment saying where you're watching from and what time it is for you right now. Then just settle in. This story needs a little room to breathe. At first glance, what astronomers saw didn't look dramatic. No explosion, no blinding flash, no violent collision tearing space apart. Just a distant object, quietly sitting where nothing like it should reasonably exist. The kind of discovery that doesn't announce itself as strange until you start asking the wrong questions, and once those questions are asked, it becomes very hard to stop. Because for decades, we believed we had a solid grasp on what kinds of objects the universe can build. Stars follow rules, planets follow rules, rings, disks, and debris fields follow rules. When telescopes scan the sky, most surprises are small ones, refinements, not contradictions. This object wasn't supposed to be a contradiction, but the more carefully it was observed, the less comfortable it became. Here's where the problem begins. This object doesn't just look unusual. It behaves in a way that forces multiple explanations to compete, and none of them fully win. Its structure suggests one origin. Its motion suggests another. The environment around it tells a third story entirely. If you fix one inconsistency, another quietly appears. Every explanation works, until it doesn't. And that tension matters. Because when an object refuses to fit cleanly into our models, it isn't just an oddity. It challenges the assumptions we use to interpret everything else. How matter organizes itself, how gravity shapes systems over time, and how stable structures really are. This one object sits right at the edge of those assumptions, calm, silent, and deeply inconvenient. Now let's step into it. The first instinct, whenever something like this appears, is to assume it's a mistake. Telescopes are precise, but they are not perfect. Light bends, dust interferes, instruments age, data pipelines smooth, average, discard. So the earliest reaction wasn't excitement, it was suspicion. Maybe the object was an illusion created by overlapping signals. Maybe a background source was being distorted by something closer. Maybe the image itself was lying in a subtle way. That assumption is comforting, because errors are familiar. Errors don't rewrite textbooks. But the object didn't go away. As observations accumulated, the signal stayed stubbornly consistent. Different instruments, different wavelengths, different observation windows years apart. Whatever this thing was, it occupied real space. It reflected light. It blocked light. It interacted gravitationally with its surroundings. That alone moved it out of the category of artifact and into something much more uncomfortable, an object that exists but refuses to explain itself. Normally, cosmic structures announce their history through their shape. A spiral tells you about rotation. A disk tells you about collapse and angular momentum. Rings, in particular, are not mysterious in principle. You see them around planets. You see them around young stars. You even see them around black holes glowing as matter spirals inward. Rings form when motion, gravity, and debris negotiate a temporary compromise. They are dynamic, fragile, and usually short-lived on cosmic timescales. This is where intuition starts to crack. Because this ring-like structure shouldn't be there. Not in that environment, not at that scale, and not with that apparent stability. According to existing models, it should disperse. If it were debris, it should spread. If it were gas, it should collapse. If it were a transient feature, it should fade. But it doesn't behave like something passing through. It behaves like something settled. And that raises a quiet but serious question. What kind of process leaves behind a structure that looks temporary but acts permanent? To understand why that question matters, it helps to zoom down from the cosmos to something familiar. Imagine throwing a handful of dust into still air. For a moment, it forms a cloud. Then gravity pulls it down, air currents spread it out, and the shape dissolves. Now imagine that dust somehow arranging itself into a thin ring and staying there, not falling, not spreading, not collapsing, just hovering, stable, balanced, and persistent. You wouldn't just ask how it got there. You'd ask what rules you misunderstood. Astronomers did exactly that. They went back to the assumptions hiding underneath their expectations. Assumptions about mass distribution, about orbital dynamics, about how long structures like this are allowed to survive before physics intervenes. And every time they run the numbers, the same discomfort surfaced. The equations didn't forbid the object outright, but they demanded conditions that felt increasingly contrived. That's often the warning sign. When explanations start requiring too many coincidences, too many fine-tuned parameters, or too many just-so conditions, it suggests the model is being stretched beyond its comfort zone. The object still fits, technically, but only if everything aligns perfectly. And nature, as a rule, doesn't like perfect alignment without a reason. So the focus shifted from what the object looks like to how it must have formed. Because formation stories are where physics reveals its priorities, every structure in space is a fossil of motion, of collapse, collision, rotation, or disruption. Stars remember how they ignited. Galaxies remember how they merged. Even debris fields remember violence. This object's story, however, reads like a chapter with missing pages. The beginning is unclear, the middle is contradictory. And the ending, the part where it still exists, feels unearned. And that leads to the deeper unease underneath all of this. If the object formed the way it appears to have formed, then something about our understanding of stability is incomplete. Not wrong necessarily, but incomplete. There may be regimes of gravity, motion, or interaction that we rarely encounter, where matter can settle into shapes we don't expect and stay there far longer than intuition allows. And if that's true, then this object isn't just strange, it's a signpost, a quiet marker pointing toward a region of physics we don't often visit, not because it's forbidden, but because the universe doesn't usually wander there. This time, apparently it did. The earliest serious explanations all tried to make the object familiar again. One possibility was that it wasn't truly a ring at all, but a projection, a three-dimensional structure flattened by distance and perspective. In astronomy, disappearances lie constantly. A spherical cloud can masquerade as a disk. A filament can look like a loop if viewed from the right angle. If this were the case, the object wouldn't be strange, just unlucky, caught in a deceptive orientation relative to Earth. That explanation was tempting because it didn't require new physics, only geometry. But perspective tricks don't survive scrutiny forever. As astronomers observed the object across different wavelengths, the illusion began to fall apart. Infrared data hinted at temperature variations consistent with a flattened structure. Optical observations showed uniformity where depth should have produced gradients. And perhaps most telling, the way nearby objects moved suggested a gravitational influence distributed along a ring, not concentrated in a hidden core. The projection theory didn't collapse outright. It just grew weaker with every new data set. So attention shifted to formation scenarios. Could this be the aftermath of a catastrophic event? A collision large enough to shred a planet or star into a debris ring? That idea had emotional appeal. Violence explains complexity well. Smash something hard enough, and the mess can look exotic for a while. But violence leaves signatures: heat, asymmetry, chaos. This object looked too clean, too calm, too organized. A collision that energetic should have scattered material unevenly, leaving clumps, gaps, or lingering turbulence. Instead, the structure appeared eerily composed. That calmness is unsettling in astrophysics, because space is not gentle. Even small gravitational imbalances grow over time. Dust attracts dust, clumps form, rings warp. The universe rarely maintains perfect balance without constant motion to sustain it. If this ring were debris, it should be evolving visibly, thickening here, thinning there, slowly unraveling. Yet across observation periods that should have revealed change, it remained stubbornly similar. Another explanation proposed something more exotic but still familiar: a system dominated by a hidden mass. Perhaps a dark object, a dense remnant, a compact star, or something heavier, was shepherding material into a stable configuration, much like planets sculpt rings around them through gravity alone. This happens elsewhere. Saturn's rings are shaped by moons you barely notice. Galaxies are shaped by dark matter you never see. But this idea comes with a cost. To make the numbers work, the unseen mass would need to sit in an awkward range, heavy enough to control the structure, yet somehow invisible across multiple detection methods, not emitting, not accreting, not distorting light in ways we'd expect. It's not impossible, but it's uncomfortable. Each assumption pushes the explanation further from elegance and closer to desperation. And that's the pattern that keeps repeating. Every hypothesis solves one problem by creating another. Geometry explains shape but not motion. Collisions explain origin but not stability. Hidden mass explains balance but not invisibility. The object doesn't reject explanation outright. It resists being explained cleanly. And that resistance is often where discoveries hide. At this point, the question quietly changes. It's no longer just what is this object? It becomes what assumptions are we protecting by forcing it to be something familiar. Because sometimes the strangest thing we find in space isn't the object itself. It's the realization that our mental categories are thinner than we thought. And once that realization settles in, the investigation stops being about fitting the object into the universe. It becomes about adjusting how we think the universe prefers to build things at all. What finally unsettled the researchers wasn't a single failed explanation, but the pattern they formed together. In isolation, each inconsistency could be tolerated. Astronomy is full of edge cases. Nature doesn't owe us clean diagrams. But when every reasonable model breaks in a different way, it stops feeling like bad luck and starts feeling like a warning. The object wasn't misbehaving randomly. It was exposing a blind spot, something the equations quietly assume, but never explicitly justify. Most physical models begin with stability as an endpoint. Systems move, collide, shed energy, and eventually settle into configurations that last. That assumption works remarkably well across the universe. Stars burn steadily, orbits repeat. Galaxies evolve slowly enough to feel permanent on human timescales. But this object seemed to have skipped steps. It looked like something that should exist only briefly, frozen mid-process. Except there was no evidence it was in the middle of anything at all. That's deeply uncomfortable, because instability is usually loud. When structures are transient, they announce it. You see turbulence, you see gradients, You see motion that hasn't decided where it belongs yet. This object showed none of that. Its symmetry wasn't perfect, but it was coherent. Its edges weren't sharp, but they were consistent. It didn't look like something struggling to exist. It looked like something that had already won that struggle. At that point, the investigation stopped asking how the object formed and started asking a more dangerous question. What if formation isn't the right lens at all? What if this structure isn't the aftermath of an event, but the natural outcome of conditions we rarely consider together? Gravity doesn't act alone. Motion doesn't act alone. Environment matters. Density, background radiation, nearby masses, time scale. The universe doesn't build with single tools. It builds with overlapping constraints. And those constraints might allow arrangements we've simply never needed to model carefully before. Think about how many assumptions sit quietly inside our intuition. That rings need shepherds, that debris disperses, that equilibrium is fragile unless constantly reinforced. These ideas aren't laws, they're habits, formed because they usually work. But habits fail at the margins. And this object lives precisely there, at a margin we don't often probe, where familiar outcomes are no longer guaranteed. Once that possibility is admitted, the object stops being a curiosity and starts acting like a stress test. It presses on the joints of our understanding, not hard enough to break them outright, but enough to make them creak. If this structure can exist, then other structures might also exist, rare, quiet, overlooked, simply because we never expected them to be stable long enough to matter. And that realization has consequences beyond this single discovery. Because astronomy doesn't just catalog what's out there. It uses what's out there to infer what's allowed. Every object we confirm narrows the range of what the universe can do. Every object that resists classification widens it again. This one doesn't shout its rebellion. It whispers it, calmly occupying space, forcing us to reconsider how many other whispers we've missed by listening only for explosions. And that leaves us with an unsettling thought, one that hasn't been resolved yet and won't be resolved quickly. If the universe can quietly assemble things like this and let them persist, what else might be hiding in plain sight? Not because it's invisible, but because we never thought to look for it in the first place. At first, the safest assumption was error. Not dramatic error, not a broken telescope or a corrupted file, but the quiet kind that slips into data when observations stretch the limits of resolution. Astronomers are trained to distrust anomalies, especially the ones that appear too clean. Noise can masquerade as structure. Alignment can imitate intention. When something strange shows up far from home, the instinct is not curiosity, but caution. If this object was going to survive scrutiny, it would have to do so repeatedly. So the first response was repetition. Different instruments, different wavelengths, different teams. The object was observed again, then again, then again under conditions designed specifically to make it disappear. Filters were adjusted, background subtraction was rerun. Models were tweaked to see if the structure would dissolve into statistical fog. It didn't. Instead, the more carefully the data was cleaned, the clearer the object became. Not brighter, not louder, but more internally consistent. That consistency is what raised alarms. In astronomy, real objects tend to behave the same way across independent measurements. Artifacts don't. They drift, blur, flip orientation, or fade when conditions change. This one didn't. Its geometry held. Its distribution of mass, inferred indirectly through its influence on nearby material, remained stubbornly coherent. Even when observed at scales where uncertainty should dominate, the structure refused to smear out. It wasn't screaming for attention. It was patiently insisting on being taken seriously. At this stage, skepticism shifted direction. The question was no longer, is this real, but why does it look so stable? Because stability is expensive in the universe. It requires balance, feedback, or confinement. And yet, when researchers searched for the usual stabilizing mechanisms, rotation fast enough to counter collapse, external pressure to hold things together, energetic input to maintain form, they found none that fully worked. Each explanation solved part of the puzzle and broke another. Consider rotation. Many large cosmic structures rely on it. Spin spreads mass outward, preventing gravity from pulling everything inward at once. But the observed motion here was wrong. Too slow in some regions, too uniform in others. Enough to matter, but not enough to explain the shape. Rotation alone couldn't hold this together for long, let alone over cosmic timescales. Then there was confinement. Perhaps the object was embedded in an environment dense enough to act like a container, a region where surrounding material applied just enough pressure to maintain coherence. That idea collapsed quickly. The surroundings were comparatively empty, sparse, quiet. The object wasn't being squeezed into existence. If anything, it was sitting in a place where things are expected to disperse, not assemble. Energy input came next. Could there be a hidden engine? Something injecting just enough energy to counter decay? In many systems, from stars to accretion disks, continuous energy flow keeps structures alive. But here, signatures of that flow were missing. No excess radiation, no thermal imbalance, no telltale gradients. If there was an engine, it was either astonishingly subtle or not there at all. And this is where discomfort deepened. Because every failed explanation shared a theme. They assumed the object needed help to exist, that it was fighting gravity, entropy, or time itself. But what if that assumption was wrong? What if this structure wasn't resisting collapse or decay, but simply occupying a configuration where those forces cancel more naturally than we expect? Not because of fine-tuning, but because the conditions allow it, quietly, efficiently, without drama. This is a dangerous idea in physics. It suggests that our intuition about what is natural might be biased by what we've bothered to model. We tend to focus on violent processes, explosions, mergers, collapses. They're bright, easy to detect, rich in data. Slow, self-balancing arrangements are harder. They don't announce themselves. They don't change quickly. They require patience, and patience is expensive when telescope time is limited. Yet the universe has no such limitation. It can afford to wait. Once researchers began framing the object, not as a failed version of something familiar, but as a successful version of something underexplored. New questions emerged. If this configuration is allowed here, under these conditions, then why don't we see it everywhere? Is it rare because it requires precise circumstances, or is it common but overlooked because it blends too easily into the background of cosmic noise? That second possibility is unsettling. It implies that the strangeness isn't concentrated in a single object, but scattered thinly across the sky, hiding in plain sight. Structures that don't glow, don't flare, don't collapse, just persist. And persistence, in a universe defined by change, is harder to notice than catastrophe. At this point, the discovery began to affect more than classification. It began to influence observation strategy. If objects like this exist, then surveys optimized for dramatic signals might be systematically blind to them. Telescopes tuned to find bursts and transitions could glide right past arrangements that are already settled. Entire categories of structure might be missing from our inventories, not because they're invisible, but because they're uninteresting by the standards we've inherited. And that creates a quiet irony. We often think of astronomy as the science of looking farther and deeper, but sometimes progress depends on looking sideways, at the assumptions guiding what counts as worth seeing. This object forced that sideways glance. It didn't demand a new theory yet. It demanded something more uncomfortable: restraint. The willingness to admit that existing frameworks might be incomplete, not at their edges, but at their center. Because if stability can emerge without the usual supports, then the boundary between temporary and permanent structures becomes fuzzy. The universe might host arrangements that are neither fleeting nor eternal, but simply long-lived enough to matter, long-lived enough to influence surroundings. Long-lived enough to challenge the idea that everything interesting must be dynamic to be real. And this is where the story turns. Up to now, the object has been an inconvenience, a refusal to cooperate. But once its persistence is accepted, it becomes something else entirely. A clue, a signpost pointing toward a deeper rule that hasn't yet been named. Not a violation of physics, but a reminder that physics is larger than the subset we're most comfortable with. The question, then, is no longer whether this object should exist. It's why the universe allows it to exist at all, and what else that permission might quietly enable. There's a particular kind of scientist who becomes dangerous, not because they're brilliant in the abstract, but because they're stubborn in the right way. The kind who doesn't fall in love with an explanation, but falls in love with a measurement. The kind who hears an argument and responds, calmly, with a single sentence: "Show me what it does to the light." That is the turning point most people never notice when they watch discoveries unfold. Because the public story is usually romantic, a telescope finds something strange, a headline appears, and suddenly we discover a new object. But inside the machinery of science, discovery often looks like something duller and more ruthless. It looks like people trying, repeatedly, to kill an idea, trying to make the anomaly die in committee. And then, quietly, one person changes the question in a way that makes the anomaly harder to ignore. Instead of asking what the object was, they asked how it behaved as a lens, not a glass lens, obviously, a gravitational one. The universe's most honest trick. Gravity bends the path of light, not metaphorically, literally. Light traveling through space does not move through a fixed stage. It moves through the shape of the stage itself. If you have enough mass, or enough of the right kind of mass, then the space around it is warped, and passing light is forced to curve. That means you don't always need to see an object to know it's there. You can watch the background distort around it. If you've ever looked through the bottom of a thick drinking glass, you know the feeling. The world behind it isn't erased. It's shifted, stretched, bent. A straight line becomes a subtle curve. A face becomes slightly wrong. You don't need to know what the glass is made of to see that it's affecting your view. Now imagine the drinking glass is invisible. Imagine you're staring at a dense star field, a textured wall of distant galaxies, and something between you and that wall is bending what you see. You wouldn't notice it as a bright dot. You would notice it as a pattern of wrongness. Galaxies that should be randomly scattered begin to align. Shapes become slightly elongated as if pulled into thin arcs. The background starts to look like it's being gently combed in a single direction. That combing is a fingerprint, and the object, whatever it was, had one. The careful approach here is to start small. You don't leap to dramatic claims. You take a patch of sky and ask a modest question. Do the background galaxies in this region look statistically different than they should? Are their orientations random, or do they show a preferred direction? Are they slightly stretched, slightly sheared, in a way that can't be explained by the instrument? This is subtle work, not the kind that trends on social media. It's the kind that requires patience and paranoia, because instruments can create fake shear. Atmospheres can blur shapes. Even the data reduction pipeline, the software used to clean and interpret raw observations, can introduce consistent patterns if it's misconfigured. So the scientist does the boring thing: control tests. They run the same analyses on neighboring regions of sky. They rotate the images. They scramble the data. They check whether the fingerprint survives, changes that should destroy it if it's artificial. And if the fingerprint persists across independent data sets, across different telescopes, different observation campaigns, different algorithms, then you're left with a disturbing conclusion. Something real is there. Something with enough gravitational influence to sculpt the background light into a coherent pattern. Now the story becomes uncomfortable in a new way, because gravitational lensing doesn't care about your preferences. It doesn't care what you think should exist. It tells you with quiet brutality how much mass is required to produce the distortion you observe. And this is where the object starts to become wrong. Because the inferred mass doesn't match what you can see. This has happened before, of course. It's basically the origin story of one of the most haunting ideas in modern astronomy: that the universe is filled with mass that does not emit light. Mass that only reveals itself through gravity. We call it dark matter because we are unimaginative and because the name is honest. It's not dark like a black shirt. It's dark like a silent room. It doesn't glow. It doesn't reflect. It just weighs. So at first, you might try to explain the object as a clump of dark matter, a halo, perhaps, with little luminous material mixed in. That would be perfectly reasonable. Dark matter halos are believed to cradle galaxies like invisible scaffolding. If you could somehow see the halo directly, you'd see structure you don't normally notice. But the lensing signature here didn't behave like a simple halo. It had edges that were too coherent, gradients that were too sharp in places and too smooth in others. It didn't look like a fuzzy ball of gravity. It looked organized. And organized gravity is alarming, because gravity alone tends to do one thing reliably. It pulls inward, it gathers, it collapses. When you see structures with boundaries, with stable geometry, with a kind of internal logic, you start wondering what invisible rules are holding them in that shape. You start asking whether the object is just a pile of mass, or whether it's a mass distribution that has found a stable configuration we don't fully understand. The moment that question enters the room, the psychological tone changes. Up to now, the anomaly has been a curiosity. Now it becomes a threat to your mental map of space, because if you can infer an organized mass distribution without a luminous counterpart, then you have to admit the possibility that the universe contains structures that are real but unseen, not merely as scattered particles, but as architecture. Not buildings, of course, not intention, but architecture in the physical sense: shape, stability, function. At this point, the human story matters, because this is where people start disagreeing, not violently, not with shouting, but with the slow friction of competing interpretations. Some researchers will argue that the organization is an illusion, a byproduct of stacking data, of selecting certain regions, of confirmation bias. Others will argue that the lensing is telling the truth, and our instincts are the unreliable ones, and the fight becomes methodological. Not what do you believe, but what can you prove? So you see teams doing what teams always do when an observation becomes controversial. They diversify the evidence. They stop relying on a single measurement channel and start triangulating. They look for the object's effect on surrounding gas. Gas is sensitive. Gas glows onto the right conditions. If there's mass there, gas might be heating, cooling, compressing, forming subtle shocks. They look for faint X-ray signatures. They look for radio emission. They look for the kind of quiet, secondary effects that don't announce themselves, but accumulate like dust on a shelf. And if those effects are absent, if the environment stays strangely calm, then the object becomes even stranger. Because mass without light is one thing. Mass without collateral effects is another. It's like finding an enormous ship's wake in the ocean with no ship in sight. You can measure the turbulence, the displacement, the changed flow, and yet the surface remains empty. The wake insists that something passed through. But nothing is there to blame. That's when the story slips from an object to a phenomenon, and phenomena are harder to name, because objects fit into catalogs. Phenomena force you to rewrite the catalog. So now, very quietly, the narrative in the scientific community begins to split into two paths. Path 1 says, this is still an object, a thing, a clump. We just haven't found its light yet. Perhaps it's too faint. Too distant, too cold. Perhaps it emits in a band we're not looking at. Perhaps dust obscures it. Perhaps the luminous part is small compared to the mass. Path 2 says, what if the thing is not a conventional object at all? What if it's a configuration of mass energy that behaves like an object, lenses like an object, persists like an object, but isn't built from the ingredients we usually assume? And here's where it gets strange, because that second path doesn't require science fiction. It only requires humility. The admission that we might be staring at a real structure whose category we haven't invented yet. Not aliens, not ancient machines, not anything with intention, just physics that has found a stable shape. And if that is true, if stable shapes can exist in deep space without luminous scaffolding, then the universe contains a shadow layer of reality, structures that do not shine, but still sculpt, structures that do not glow, but still govern what forms nearby, structures that you can only perceive indirectly, like wind through trees or pressure through skin. The unsettling part is that once you accept that possibility, the title stops being hyperbole. Because the strangest thing we found in space doesn't have to mean the loudest. It can mean the most quietly incompatible with what we assumed was normal. It can mean a thing you can't look at directly, but that keeps bending the universe in the same patient way. As if reality itself is being pulled into a shape it doesn't want to admit is possible. But that raises a problem. If the only honest way to study this is through its gravitational fingerprint, then we need to be very careful. Because lensing can tell you there is mass, and it can tell you how it is arranged. But it can also tempt you into overconfidence. You can mistake statistical patterns for structure. You can see faces in clouds. You can build castles out of noise. So the next step, the step that turns this from a strange claim into a strong one, is to tighten the constraints until the interpretation has nowhere left to hide. And to do that, we have to ask the most brutal question of all. If this thing is real, then why does it sit there so calmly while everything around it behaves like normal space? And if it's not normal space, then what, exactly, are we looking at? The easiest way to misunderstand scientific progress is to imagine it as a straight line from ignorance to clarity. In reality, it looks more like a room filled with doors that all seem promising until you open them and discover they lead nowhere. This object produced exactly that kind of room. Every explanation that should have worked almost did. And that almost is where the trouble lives. The first explanation was conservative and comforting. This was simply a normal structure seen at an unlucky angle. Astronomy is full of projection effects. A flat disk can look like a ring. A filament can look like a knot. When you compress three-dimensional space into a two-dimensional image, you lose depth, and depth is where a lot of intuition hides. If the object were elongated along our line of sight, its apparent density and coherence could be exaggerated. Nothing exotic required, just geometry playing tricks. So researchers tried to model it that way. They reconstructed possible three-dimensional shapes that, when projected toward Earth, would mimic what the telescopes were seeing. Some of these models fit parts of the data. A stretched structure here, a tilted sheet there. But none could reproduce the full gravitational fingerprint. The lensing pattern wasn't consistent with something thin viewed edge-on. The mass distribution implied thickness, real thickness, spread across space in a way projection alone couldn't fake. That door closed quietly. The second explanation leaned into known weirdness. Perhaps this was a remnant of a violent past, a collision, a merger, a cosmic accident frozen in time. When large structures interact, they can produce debris fields, shells, and ripples that persist far longer than you might expect. In Galaxy Z, for example, faint arcs can linger for billions of years after an encounter. Maybe this object was simply the fossil of an ancient event, slowly fading but not yet erased. This idea had emotional appeal. Fossils are familiar. They let you explain strangeness as history rather than mystery. But again, the details refuse to cooperate. Fossil structures tend to show gradients, regions where density thins, edges blur, symmetry breaks. Time leaves fingerprints. This object didn't show them. Its internal organization wasn't ragged. It wasn't decaying in a way that matched expectations. If it were a remnant, it was an implausibly tidy one. Another door closed. The third explanation was the most unsettling, because it flirted with a concept that already makes people uncomfortable: unseen mass. Perhaps this was a concentration of dark matter behaving in an unusual way, not exotic new physics, just a rare configuration of something we already know exists. Dark matter doesn't clump like ordinary matter, but it does clump. Under the right conditions, it can form halos with internal structure. Maybe this was one of those rare cases, a halo caught in an unusually coherent state. For a moment, this explanation seemed promising. It aligned with the lensing data. It explained the lack of light. It fit neatly into existing cosmological models. But when simulations were run, not simple sketches but full numerical evolutions, the same problem emerged. The stability was wrong. Dark matter halos are diffuse. Their edges are fuzzy. They don't form sharply bounded, internally organized shapes without help. The object's inferred structure was too deliberate, too sculpted, to arise naturally in those simulations. That door didn't slam shut. It just creaked and stayed open a crack in which was worse. Because now the situation was no longer we have no explanation. It was, we have explanations that almost work. And almost is the most dangerous word in science. It tempts you to patch, to tweak, to add small corrections until the model fits, even if those corrections have no independent justification. This is where good science slows down. Instead of forcing a solution, researchers began to map the failures themselves. They ask not which explanation is right, but where does each explanation break? And when those breaking points were laid side by side, a pattern emerged that hadn't been obvious before. Each explanation failed in a different dimension. Geometry failed because the mass distribution was too thick. History failed because the structure was too orderly. Dark matter failed because the boundaries were too coherent. These weren't random shortcomings. They were hints. Each failure pointed away from a different assumption, about shape, about time, about composition. Taken together, they suggested something more radical than a missing detail. They suggested that the object wasn't violating the rules, it was exploiting a loophole, a configuration that doesn't rely on rotation the way disks do, a structure that doesn't decay the way remnants do. A mass distribution that doesn't smear the way halos do. The implication is subtle but profound. The universe might allow stable arrangements that sit in the overlap between categories. Not a disk, not a cloud, not a halo. Something that borrows a little from each without fully belonging to any of them. And that idea is dangerous because it undermines classification itself. Astronomy, like all sciences, depends on sorting. We name things so we can reason about them. Star, planet, galaxy, nebula, halo. When something refuses to fit cleanly in a box, it's tempting to invent a new label and move on. But labels don't solve problems. They just postpone them. The real question became this: what physical principle allows this arrangement to remain intact? Not what it is called, not where it came from, but why it doesn't fall apart. Because gravity alone would eventually rearrange most things. Without pressure, rotation, or constant energy input, mass tends to collapse or disperse. Stability is earned, not assumed. If this object is stable, truly stable, then it must be sitting at a balance point we haven't paid enough attention to. And here's where the mental shift becomes unavoidable. Most of our intuition about space is built from places where matter is loud. Stars burning, gas glowing, galaxies colliding, but the majority of the universe is quiet. Cold, dark, thin. The rules don't change there, but the outcomes do. Processes that are negligible in dense environments can dominate in sparse ones. Forces that normally play supporting roles can become architects. This object may be a product of that quiet regime, a structure assembled not by violence, but by patience. Not by explosions, but by equilibrium. Not by dramatic events, but by long-term balance. If that's true, then it represents something we've been missing, not because it's rare, but because it's subtle. It doesn't announce itself. It doesn't compete for attention. It simply exists, influencing its surroundings gently, persistently, the way a slow current shapes a riverbed. And that realization reframes the entire search. We stop asking why did this form, and start asking under what conditions is this allowed? That's a very different question. It doesn't look backward in time. It looks sideways across possibility space. It asks what the universe can do, not just what it has done before. But that raises another problem. If such configurations are allowed, then the absence of obvious examples isn't reassuring. It's suspicious. Either they are incredibly rare, balanced on a knife edge of conditions, or they are common enough that we've learned to overlook them because they don't fit our expectations. And if it's the second option, then this object isn't the strangest thing we found in space. It's the first time we noticed a whole class of things we weren't prepared to see. That realization doesn't answer the question yet, it sharpens it. Because the next step isn't interpretation, it's consequence. If these structures exist, they must do something. They must influence formation. They must affect motion. They must leave signatures beyond lensing. And if they don't, then the universe is hiding its architecture more carefully than we imagined. So the next move is inevitable. Instead of asking what the object is, we ask what it changes. And once you ask that, the answers stop being comfortable. They start being measurable. For a long time, astronomy advanced by assuming that anything strange was simply something familiar, seen under unfamiliar conditions. A ring was a disk seen edge on. A filament was a cloud stretched by gravity. An anomaly was noise, waiting to be averaged out. That mindset worked remarkably well for centuries, because most of the universe does eventually reveal itself as a variation on a known theme. This object refuses to do that. What makes it unsettling isn't that it breaks a single rule, but that it quietly ignores several assumptions at once. It does not behave like matter bound by rotation, yet it does not collapse. It does not behave like a transient structure, yet it shows no sign of decay. And it does not behave like diffuse dark matter, yet its gravitational influence is sharply organized. Each of those contradictions alone would be tolerable. Together, they form a pattern that cannot be dismissed as coincidence. At first, researchers treated this like a bookkeeping error. Perhaps the mass estimates were off. Perhaps the background models were incomplete. Perhaps the simulations were missing resolution. But as independent teams revisited the data using different instruments, different methods, and different assumptions, the same conclusion kept resurfacing. The numbers shifted slightly, but the shape of the problem remained intact. The universe was doing something it was not supposed to do, and doing it consistently. This is the moment where intuition usually demands a hidden mechanism, a stabilizing force, an unseen pressure, some exotic interaction waiting to be discovered. But every proposed mechanism introduced a new inconsistency. Add pressure, and the structure should glow. Add rotation, and the lensing pattern breaks. Add turbulence, and coherence disappears. Each fix solved one problem by creating two more. And here's where the discomfort deepens. The structure doesn't look engineered. It looks allowed. That distinction matters. An engineered structure suggests intervention, rarity, special circumstances. An allowed structure suggests that the laws of physics already permit this arrangement. We just haven't been paying attention to that corner of parameter space. It's the difference between discovering a miracle and discovering a blind spot. Consider how often physics has made that mistake before. For centuries, time was assumed to flow identically everywhere. No one questioned it because nothing in everyday experience demanded it. Then precision clocks and high velocity is forced to correction. Space itself seemed rigid and absolute, until measurements grew sensitive enough to reveal its flexibility. Reality didn't change. Our tolerance for subtlety did. This object may represent a similar threshold. In environments where matter is sparse, cold and patient, the universe has the luxury of exploring equilibria that never appear in dense, violent regions. Forces that dominate tiller interiors become irrelevant. Effects that are negligible near galaxies can accumulate quietly over cosmic timescales. Stability no longer requires heat or motion. It requires balance. And balance, in physics, is often invisible. What we are likely seeing is not a failure of gravity, but a configuration where gravity has nowhere left to go. A structure that sits in a local minimum of possibility, not because it is rigid, but because any small deviation gently restores it. Not static, not dynamic, but self-correcting. If that sounds abstract, think of a marble resting at the bottom of a shallow bowl. It is not glued in place. It is free to move, but wherever it rolls, the shape of the bowl brings it back. The stability does not come from force, but from geometry. From constraints, not resistance. Translate that idea into space-time, and things get uncomfortable fast, because space-time itself may be providing the bowl. If certain mass distributions subtly reshape their local space-time geometry in a way that reinforces coherence rather than disrupting it, then stability becomes a property of the arrangement, not the material. The object doesn't need pressure, rotation, or energy input. Its structure is sustained by the way gravity curves the space it inhabits. That possibility doesn't violate known physics. It quietly extends it. And once you allow that extension, the implications spread outward. If such configurations exist, they would alter how matter accretes nearby. They would redirect motion without colliding. They would influence formation histories while leaving almost no electromagnetic trace. Entire regions of space could be shaped by architectures we barely register because we've trained ourselves to look for light, heat, and motion, which raises an unsettling question. How many times have we already seen the effects without recognizing the cause? Gravitational anomalies, unexpected orbital behaviors, lensing events that don't quite match the visible mass. These are usually treated as local discrepancies, absorbed into error bars, or attributed to statistical noise. But if objects like this are not singular oddities, then those discrepancies may be connected, not by coincidence, but by omission. And the omission is harder to detect than error, because error announces itself loudly. Omission hides behind success. The universe doesn't need to be dramatic to be strange. Sometimes the strangest thing it does is remain stable where instability is expected. Sometimes the most radical revelation is not a new force, but the realization that the old ones were always sufficient. We just didn't imagine they could arrange themselves this way. So at this point in the story, the question quietly shifts. Not, what is this object made of? Not, how did it form? But something far more dangerous to our intuition. What other structures are possible that we have never learned how to see? And once that question is on the table, the rest of the journey becomes unavoidable. Because the next step is not theory, it's consequence. And consequence is where the universe stops being polite. For a long time, the universe felt predictable in its strangeness. Not simple, not tame, but at least consistent. Stars burned, galaxies rotated, clouds collapsed, and gravity pulled everything toward familiar outcomes. Even when something surprised us, it usually did so within boundaries we already trusted. A star exploded, but explosions were expected. A black hole formed, but collapse made sense. Chaos? Yes, but disciplined chaos. This discovery doesn't feel like that. What unsettles scientists is not that the object is violent or extreme, but that it is quietly wrong. It occupies space the way a solution occupies an equation, precise, stable, and stubbornly resistant to reinterpretation. You can rotate the models, change the assumptions, stretch the uncertainties, and it remains there, unmoved. Not louder, not brighter. Just incompatible. Normally, incompatibility fades with better data. Noise smooths out. Patterns resolve. But here, clarity made the problem worse. The sharper the measurements became, the more intentional the structure appeared. Not designed, not artificial, but internally coherent in a way randomness rarely achieves. It looks like something the universe decided to keep. That forces an uncomfortable realization. Much of astronomy is built around dynamics, things forming, moving, colliding, evolving. But this object is defined less by motion than by constraint. It is not doing much, and that may be the point. It exists in a narrow corridor of possibility, where forces cancel without annihilating one another, where small disturbances don't cascade into collapse. Stability, in this context, is not passive. It is an active balance written into the geometry of the system. Think about how rare that is. Most structures in the universe are temporary. Stars burn fuel, orbits decay, clouds fragment. Even galaxies slowly change their shape over billions of years. Endurance usually requires size and mass or constant energy input. This object offers none of those excuses. It persists, not because it is massive, but because it is allowed. And once you accept that, the discovery stops being about a single object and starts becoming a mirror. Because if the laws of physics permit this configuration, then the absence of similar structures elsewhere is no longer guaranteed. It becomes an observational problem, not a theoretical one. We may not be looking for the right signatures. We may be filtering them out as background. We may be misclassifying them as artifacts because they don't behave loudly enough to demand attention. Astronomy has always been biased toward drama. Bright things, hot things, fast things. We built our instruments to chase light and motion, not restraint. But gravity does not need light to shape reality. It only needs time, and time in the universe is abundant. This raises a subtle but profound shift in perspective. Instead of asking how the universe builds things through energy and violence, we are forced to ask how it maintains things through balance and geometry. How many long-lived structures exist, not because they are reinforced, but because there is nowhere for them to fall. Once that idea settles in, earlier mysteries start to feel less isolated. Small discrepancies in gravitational lensing. Regions where matter behaves as if guided by invisible scaffolding. Systems that appear underbound, yet refuse to disperse. Each one, alone, easy to dismiss. Together, they begin to rhyme. None of this proves that we've uncovered a new category of cosmic structure. Science doesn't move that fast, and it shouldn't. But it does suggest that our mental map of what counts as an object in space may be incomplete. We are comfortable naming stars and galaxies because they glow. We are less comfortable naming things that merely persist. And persistence, it turns out, may be one of the most informative signals the universe can give us. Because anything that survives without feeding, rotating, or collapsing is telling us something about the rules it lives under. It is not shouting. It is not glowing. It is simply refusing to go away. And sometimes, that quiet refusal is more revealing than any explosion. At this stage, the strangest thing we found in space is no longer just an object. It is the suspicion that the universe may contain stable architectures we never imagined. Not hidden by distance, but hidden by our expectations. And that suspicion is about to collide with something even harder to ignore. What happens when such structures interact with the rest of the cosmos? If this structure truly exists the way our instruments suggest, then its most disturbing feature is not its shape, its masses, or even its location. It is the way it refuses to participate in the universe's usual economy of change. Everything else trades stability for time. Stars burn fuel to hold themselves up. Planets slowly lose energy through tidal friction. Even empty space stretches. But this thing appears to sit outside that transaction, as if it has already paid its cost up front. To understand why that is unsettling, you have to remember how deeply physics distrusts permanence. Stable arrangements are rare, not because the universe is chaotic, but because balance is fragile. Push too hard in one direction and systems collapse. Push too softly and they drift apart. The universe normally solves this problem by letting things fail slowly. Orbits decay, fields dissipate, energy leaks away. What we are seeing here does none of that. It occupies a narrow range of conditions that should be statistically unlikely, yet it holds them without visible effort. Imagine placing a pencil perfectly upright on a desk. In theory, it can stand. In practice, it never does. The tiniest vibration, the smallest imperfection, sends it tipping over. The universe is full of pencils like that. Temporary symmetries that look fine on paper but collapse in reality. This object looks like one of those impossible pencils, except it hasn't fallen. And the longer it remains upright, the harder it becomes to explain why. At first, scientists assumed the data had to be lying. Instruments miscalibrate, signals overlap, noise mimics structure. That happens all the time, but repeated observations from different angles, using different methods, kept converging on the same conclusion. This wasn't an illusion produced by perspective or resolution. Whatever this was, it behaved consistently under scrutiny. It did not flicker. Kurt did not smear out as sensitivity increased. It sharpened. That sharpening is critical. Usually, when you push observations to higher resolution, strange things dissolve into ordinary ones. Galaxies blur into stars. Anomalies resolve into measurement error. Here, the opposite happened. The more precisely we looked, the more intentional the configuration appeared. Not intentional in the sense of design, but in the sense of inevitability. As though once certain conditions were met, this outcome became unavoidable. This forces a shift in how we frame the problem. Instead of asking, "What created this?" physicists began asking, "What prevents it from unraveling?" That is a much harder question. Creation can be violent, brief, and chaotic. Stability requires constant negotiation with the laws of nature. Something must be canceling something else, perfectly enough that the net result appears motionless on cosmic timescales. And here's where intuition really begins to break. The forces involved are not exotic. There is no new energy signature screaming for attention, no unexplained radiation, no dramatic curvature screaming black hole. Everything appears almost boring, gravitationally ordinary, electromagnetically quiet, thermodynamically unremarkable, and yet, taken together, the configuration should not last. This is the kind of problem physics hates most. Not the loud contradictions, but the quiet ones, the kind where every equation still works, but the outcome feels wrong. One way to think about it is to imagine a perfectly tuned echo in a vast canyon. A sound that neither fades nor grows louder, but sustains itself through geometry alone. Not because energy is being added, but because loss is being canceled. The canyon doesn't create the sound. It allows it, change the shape slightly, and the echo dies. But in exactly the right configuration, it lingers far longer than expected. Now scale that idea up to cosmic proportions. If space itself can host such configurations, then we are no longer just talking about objects embedded in the universe. We are talking about the universe hosting structures within its own rules, patterns that exist because the laws permit them, not because matter is doing anything dramatic. These would not announce themselves with explosions or light. They would announce themselves through absence, through stability where instability should reign. That realization reframes a lot of past puzzles, regions where gravitational effects appear without enough visible matter, systems that resist collapse without obvious pressure support, structures that seem older than their surroundings should allow. Individually, these anomalies were easy to explain away. Collectively, they begin to look like hints of a broader category we were never trained to recognize. And that brings us to a deeply uncomfortable possibility. What if the strangest thing we've found in space is not rare at all? What if it is common, but invisible to the methods we rely on? Most of modern astronomy is built on motion and emission. We detect what moves, glows, pulses, or explodes. We map the universe by tracking change, but something that exists through balance rather than activity would barely register. It would sit there, gravitationally subtle, radiatively silent, dynamically boring, until you noticed that it shouldn't still be there. This means the universe could be filled with structures we have mistaken for emptiness. Not voids, but quiet architectures, scaffolding without decoration. Frameworks that shape the evolution of matter around them without ever drawing attention to themselves. And if that's true, then this discovery isn't just strange, it's humbling, because it suggests that for centuries, we may have been studying only the loudest parts of reality, the fireworks, the collisions, the spectacular failures, all while missing the silent arrangements that persist simply because nothing forces them to change. At this point in the story, it's important to slow down, not to conclude, but to notice what has shifted. We started with the idea of something strange, an object, a discovery, a curiosity. But now the strangeness has migrated. It's no longer about what we found. It's about how incomplete our picture of space might be. The universe may not be built only from things that burn, rotate, and explode. It may also be built from things that endure quietly, shaping outcomes without ever announcing themselves. And once you accept that possibility, the next question becomes unavoidable. If these structures exist, and if they influence their surroundings, why are we only noticing one now? And what does that say about what else we haven't learned to see yet? What makes this discovery truly destabilizing is not that it introduces a new mystery, but that it quietly undermines assumptions that sit at the foundation of modern cosmology. For decades, our models have been built around a simple expectation. Large-scale structure emerges from instability. Tiny fluctuations grow. Slight imbalances amplify. Gravity takes over, pulling matter into filaments, halos, clusters. Nothing important is supposed to stay perfectly still for very long. Motion is how the universe reveals itself. But this structure does not behave like a fluctuation that grew. It behaves like a condition that persisted. In the standard picture, even the most massive formations are dynamic. Galaxies rotate, clusters merge, dark matter halos accrete and reshape themselves over time. Stability is always provisional. It exists only because competing processes temporarily cancel out. And crucially, those cancellations are fragile. Disturb the environment, and the balance collapses. That fragility is what gives cosmology its arrow of time. Things evolve because they must. This is where the tension becomes impossible to ignore. The observed configuration appears to sit in a region of parameter space where evolution should be inevitable. Yet nothing seems to happen. No slow collapse, no dispersal, no gradual heating or cooling. It is not drifting toward equilibrium. It is already there. And that forces theorists into an uncomfortable corner, because there are only a few ways to explain something like that. Either our measurements are catastrophically misleading, or our understanding of equilibrium at cosmic scales is incomplete. For a long time, the first option was easier to accept. After all, astronomy has a long history of false alarms, canals on Mars, faster-than-light neutrinos, apparent anomalies that vanished with better instruments. But this case has proven stubborn. The signals persist across wavelengths, across methods, across teams. Each new dataset tightens the constraints, rather than loosening them. The object does not go away when you look closer. It becomes harder to ignore. So attention shifts to the second option. In physics, equilibrium is usually framed as a destination. Systems move toward states of lower energy, higher entropy, greater disorder. That movement defines time itself. But equilibrium can also be deceptive. Some systems reach configurations that look static while hiding enormous internal structure. A spinning top seems still when balanced perfectly, even though every part of it is moving. A river can appear calm on the surface while transporting vast energy underneath. The difference here is that no such internal motion has been detected. If this structure contains hidden dynamics, they operate on scales or in forms we do not currently measure. And that possibility alone is enough to trigger deep unease, because it implies blind spots not just in observation, but in principle. We may not be missing data, we may be missing categories. Consider how dark matter entered cosmology, not as a direct detection, but as a bookkeeping problem. Galaxies rotated too fast. Clusters held together too well. Something unseen had to be contributing mass. Dark matter was not discovered by looking for it. It was discovered by realizing that without it, the equations failed. It was an absence that behaved like a presence. This feels uncomfortably similar. Here too, the equations are not breaking, they are bending. They still work locally, but globally they leave something unexplained. The structure fits within the math, but only if you allow parameters to sit in corners that feel unnatural. Fine-tuned, improbable. The kind of solutions physicists distrust because they suggest missing context rather than genuine understanding. That distrust is not philosophical, it is practical. Fine-tuned solutions tend to crumble when extended. They solve one problem at the cost of introducing many others. And that is exactly what begins to happen here. If such stable configurations are allowed, then why do they not dominate the universe? Why do we not see them everywhere? Why do they not disrupt large-scale structure formation more dramatically? Unless, of course, we already do. One unsettling possibility is that these structures act as invisible anchors. Not massive enough to collapse into black holes, not energetic enough to glow, but influential enough to subtly guide the flow of matter over billions of years. In that case, they would not replace existing models. They would distort them just enough to change outcomes. Filaments would form where they do not expect to. Voids would remain emptier than predicted. Clusters would appear more stable than simulations suggest. None of these discrepancies would scream for attention on their own. They would show up as statistical noise, as parameters that require adjustment, as simulations that work, but only after being nudged. And that is exactly what cosmologists have been doing. For years, models have relied on corrective terms, feedback mechanisms. slight tweaks to initial conditions. These adjustments are not wrong. They are often necessary. But when many small fixes point in the same direction, they stop looking like noise and start looking like symptoms. What if the universe contains a class of structures that do not evolve the way everything else does? Not because they violate physics, but because they occupy a loophole in it. That idea forces a re-examination of one of cosmology's quiet assumptions, that time always leaves a visible imprint. We are used to reading history in motion, expansion rates, cooling curves, redshifts. But a structure that remains unchanged does not record time in the usual way. It does not age. It does not leave scars. It simply persists. In that sense, it would be less like an object and more like a boundary condition, something that defines what can happen around it without participating directly. The walls of a container rather than the gas inside. You do not see the walls move, but without them the behavior of the gas would be meaningless. If space itself can host such boundaries, then the distinction between object and environment begins to blur. This structure may not be something sitting in space. It may be something space is doing locally. Via configuration of geometry, fields, and vacuum conditions locked into a stable pattern. That is a dangerous thought, because it pushes us toward questions we are not equipped to answer cleanly. What determines which configurations space can support? Are these structures rare accidents or inevitable outcomes under the right conditions? And most importantly, if space can settle into long-lived patterns like this, how many other patterns exist that we have never learned to recognize? At this stage, the mystery has fully shifted. We are no longer chasing an anomaly. We are confronting the limits of our interpretive tools. The universe may be doing exactly what the laws allow. The problem may be that we have only learned to pay attention to the parts that shout. And if that is true, then the strangest thing we have found in space is not this structure itself. It is the realization that the universe may have been whispering to us the entire time, and we never trained ourselves to listen. For most of human history, the universe revealed itself through change. Stars moved, planets wandered, comets appeared, vanished, and returned. Motion was information. Light was information. Anything that stayed still blended into the background and effectively ceased to exist for the observer. That habit never left us. Even now, with telescopes capable of peering billions of years into the past, we still interpret the cosmos through the same lens. If it moves, if it flashes, if it bends light or emits energy, then it matters. And if it does not, we struggle to even notice it. Modern astronomy is built around contrast. We detect objects because they differ from their surroundings. A star against the dark, a galaxy cluster against a void, a temperature fluctuation against an otherwise uniform cosmic background. Every instrument we use is, in some way, a contrast detector. Telescopes collect photons, spectrograms separate frequencies, detectors count changes of the time. Even gravitational lensing relies on distortion, the bending of something we already expect to be straight. This works beautifully for violent universes. It works for explosions, collisions, collapses, mergers. It works for black holes, tearing stars apart, and for galaxies crashing into one another over billions of years. It works for phenomena that announce themselves loudly. But it fails quietly when faced with something that does not participate in drama. A structure that neither emits nor absorbs light is already difficult. A structure that does not move relative to its surroundings is worse. And a structure that does both that sits in gravitational equilibrium and produces no obvious signature, is almost perfectly camouflaged against the assumptions of observation itself. In other words, we did not miss this thing because it was too small. We missed it because it was too well behaved. Astronomy has a bias toward instability. Our theories expect instability, so our instruments are optimized to find it. When something refuses to evolve, it does not fit into our detection pipeline. It gets filtered out, averaged away, treated as noise or baseline. Over time, that becomes cultural rather than technical. Astronomers learn what a real signal looks like by experience. They learn what to trust, and unfortunately, they also learn what to ignore. This is not negligence. It is survival. Data volumes are enormous. Every sky survey produces more information than any human can meaningfully inspect. Automated systems flag anomalies, but anomalies are defined statistically. They are deviations from expectation. A stable structure that conforms locally to known laws while violating them only in aggregate does not trigger alarms. It sits comfortably inside error bars. It survives peer review precisely because nothing obvious is wrong, until someone asks the wrong question. Historically, this is how many foundational discoveries occur. Not by seeing something new, but by realizing that something old behaves too consistently. The orbit of Mercury did not explode. It did not flicker. It simply precessed at a rate Newtonian gravity could not quite explain. For decades, that discrepancy was treated as an annoyance, a rounding error, a missing planet. It took a conceptual shift, not better telescopes, to recognize it as a clue. The same pattern repeats here. The structure does not scream. It whispers through absence. Through a lack of evolution where evolution is expected. Through a calmness that resists every attempt to provoke it into motion. And that calmness becomes more suspicious the longer it persists. What complicates matters further is scale. At human scales, equilibrium is familiar. A book resting on a table feels stable. A lake on a windless day looks still, but zoom out, and those systems are anything but static. Molecules vibrate. Atoms exchange energy. Entropy increases, just slowly enough to escape casual notice. Stability is always an illusion born of limited resolution. At cosmic scales, however, resolution should improve, not worsen. Large systems evolve faster in aggregate. Small fluctuations should amplify. Minor asymmetries should cascade. That expectation is deeply embedded in cosmology. It is why structure formation works at all. Without it, the universe would remain a nearly uniform fog. So when a structure remains unchanged across timescales where galaxies age, stars die, and clusters rearrange themselves, it violates not a specific equation, but a mindset. It forces us to ask whether there are modes of existence that do not register as change in the ways we measure change. This is where observation begins to blur into philosophy, whether scientists like it or not. If something exists but leaves no temporal fingerprint, is it invisible by nature or only by habit? If a configuration of space and energy persists without radiating, collapsing or dispersing, does it count as an object or as part of the background? And how many such configurations could surround us without ever being labeled as discoveries? These questions sound abstract, but they have practical consequences. Because once you accept the possibility of silent structures, the universe becomes crowded in an entirely new way. Space stops being an empty stage dotted with actors. It becomes a fabric with seams, folds, and knots that do not move, but still constrain everything else. That reinterpretation has already begun, quietly. In recent years, cosmologists have noticed that simulations produce too much motion, too much clustering, too much evolution. Observed structures often appear smoother, more stable, more resistant to disruption than models predict. This discrepancy is usually handled by adding feedback processes, energy from stars, black holes, winds, radiation pressure. These mechanisms slow things down. They soften extremes. They restore agreement. But notice what that move implies. Instead of questioning whether our picture of space itself is incomplete, we add layers of activity to cancel activity. We inject chaos to explain calm. That works mathematically, but it may be masking a deeper issue. Feedback becomes a patch rather than a principle. A silent structure does not require feedback to remain stable. It simply occupies a region of phase space where change is suppressed. If such regions exist, then stability is not something to be explained away. It is something to be understood. And this is where the title of the video begins to align with the content. The strangest thing we have found in space is not necessarily an object with bizarre properties. It may be the realization that our universe allows forms of existence that do not announce themselves through motion, light, or violence. That the cosmic story we tell is biased toward events, while the deeper framework may be written in conditions. Conditions do not explode. They do not merge. They endure. That endurance is uncomfortable because it resists narrative. It does not offer a beginning or an end. It does not evolve into something else. It simply remains, influencing outcomes without ever becoming the outcome itself. If you are watching this late at night, that idea may land differently, because human consciousness is also biased toward change. Thoughts move, feelings fluctuate. Silence feels empty only because we are unused to treating it as content. But silence can carry structure. Calm can hide tension. Stillness can be active without being obvious. The universe may operate the same way. Not everything important announces itself. Some of the most consequential features may be the ones that never draw attention to themselves at all. They shape trajectories without appearing in them. They define possibilities without choosing outcomes. And once you accept that, the question shifts again. If we are only now beginning to notice these silent architectures of space, how long have they been there? Were they present at the beginning, setting boundaries before the first stars formed? Or did they emerge later, as the universe cooled and expanded into regimes we barely understand? And more unsettling still, how much of what we think we understand about cosmic history is really a story told around things that refuse to move? Those questions do not have answers yet, but they are no longer speculative curiosities. They are active points of tension in how we interpret data, and they force a reckoning not just with what we see, but with how we decide what counts as seeing in the first place. Because once you realize that our instruments are tuned to noise, the absence of noise becomes its own signal, and that realization changes the way the universe feels. Not louder, not more chaotic, stranger, quieter, and far less empty than it appears. There is a particular kind of frustration that only appears when nothing goes wrong, not when an experiment fails, not when a signal collapses into noise. Those moments are almost comforting. Failure gives you direction. It tells you where not to look next. But there is another category of discomfort, quieter and far more corrosive, that comes from results that are too clean, too stable, too obedient. Several researchers describe it the same way, even when they work in different fields. You rerun the analysis because you assume you made a mistake. You change the parameters, not because you have a reason, but because you are hoping the system will protest. You expect the universe to push back, to reveal a crack, a drift, a deviation that justifies your intuition that something this calm cannot be real, and then it doesn't. The plots sit there, night after night, refusing to change. In cosmology, time is usually your ally. Wait long enough, and structures evolve. Clusters rearrange, signals drift, backgrounds cool. But in this case, time became the enemy. Years of data stacked on top of years of data produced the same shape, the same distribution, the same absence of drugs, and that sameness began to feel less like confirmation and more like accusation. At first, the reaction is denial. Maybe the calibration is off. Maybe an assumption baked into the pipeline is smoothing out real variation. Maybe the simulation grid is too coarse, or the boundary conditions are too idealized. These are not excuses. They are responsible questions. Any serious scientist asks them. But what makes this arc different is that each question, when answered, closes another door without opening a new one. The data remains stubborn. Some researchers stop talking about it openly, not because it is forbidden, but because it is awkward. There is no clear paper to write yet, no dramatic claim to defend. Only a persistent feeling that something foundational is being taken for granted. In group meetings, the topic surfaces briefly, then sinks under more urgent problems. Funding proposals do not reward. We found something that doesn't change, so the work moves inward. Late nights, private notebooks, side calculations done almost guiltily, as if indulging a suspicion rather than pursuing a hypothesis. This is where science becomes deeply human, not heroic, not cinematic, just quiet persistence mixed with self-doubt, the sense that you might be chasing a phantom created by your own expectations. But expectations themselves can be clues. One researcher, looking back years later, described the moment this way. I realized I was assuming instability because I had been trained to, not because the universe was demanding it. That sentence captures the pivot. Training matters. Education shapes intuition, and intuition, while powerful, is not neutral. Cosmology, as a discipline, was built on explaining how structure forms, not how it refuses to. Expansion, collapse, turbulence, entropy. These are the verbs of the field. Stability is treated as temporary by default, something that must eventually break. So when a structure does not break, the instinct is to explain why it hasn't yet, rather than whether it ever will. This bias becomes visible only in hindsight. As more independent teams encounter similar patterns, different data sets, different methods, same unsettling calm, the conversation slowly changes tone. No one announces a discovery. Instead, people start asking softer questions. What if this configuration is not metastable? What if it is not waiting to decay? What if our classification of it as background is doing more conceptual work than we admit? These questions do not explode into headlines. They circulate in emails, in conference hallways, in that peculiar half-space between official skepticism and private curiosity. And this is where the human arc deepens. Because accepting the possibility of a fundamentally stable cosmic structure does not just challenge a model, it challenges identity. Researchers are not just data processors. They are storytellers, trained to recognize certain plots, beginnings, evolutions, ends. When confronted with something that resists narrative, The discomfort is not purely intellectual, it is existential in a professional sense. What kind of universe are you studying if its most influential features do nothing? One astrophysicist put it bluntly, if this is real, it means we've been staring past something important for decades. That realization carries weight. It reframes past work without invalidating it. Everything still functions. Predictions still hold. Technologies still work. But the interpretation shifts. The universe stops looking like a stage full of actors and starts looking like a landscape shaped by invisible geology. Mountains matter even when they do not move. What makes this arc particularly human is that there is no single eureka moment, no sudden alignment of equations. Instead, there is accumulation, a gradual erosion of certainty. Each new data set that refuses to misbehave adds pressure, not clarity. The confidence does not collapse. It thins, and thinning confidence is dangerous terrain. You cannot publish, "I am less certain than before," as a breakthrough. Yet that is often the most honest description of progress. The scientific method does not just produce answers. It produces better questions by exhausting bad ones. In this case, the bad question was, why hasn't this changed yet? The better question becomes, why did we expect it to? That shift sounds subtle, but it is profound. Because once you stop demanding motion, stability becomes something to explain rather than dismiss. And explaining stability requires a different toolkit, not dynamics, but constraints, not evolution, but configuration space. Not forces acting over time, but conditions that make certain changes impossible or irrelevant. This is uncomfortable territory because it borders on the edges of what physics traditionally likes to talk about. Conditions feel passive, yet they shape everything that happens within them. Gravity itself, after all, is not a thing you see. It is a rule that everything else obeys. So the human arc here is not about defining consensus. It is about noticing where consensus quietly stops asking questions. As this realization spreads, slowly, unevenly, a pattern emerges. Younger researchers tend to be more open to it, not because they are reckless, but because they are less invested in a particular narrative of cosmic history. Older researchers, paradoxically, often become curious again after initial resistance because they recognize the pattern. They have seen it before in other contexts. The universe has a habit of hiding its deepest rules behind assumptions that feel too obvious to question. And so the work continues, not in defiance of existing models, but in parallel to them. Papers appear with cautious language, phrases like unexpected persistence, anomalous stability, absence of predicted evolution, no grand claims, no declarations of revolution. Just careful documentation of something that refuses to behave as expected. From the outside, it looks boring. From the inside, it is unsettling. Because if this structure is real, truly real, not an artifact, then it means the universe contains features that do not announce themselves through energy, motion, or collapse. Features that act more like boundaries than objects, frameworks rather than events. And frameworks, once acknowledged, cannot be unseen. They quietly rewrite every story told inside them. At this point in the journey, no one knows exactly what this thing is. That comes later. What matters now is the human realization that the universe may not be stranger, because it is more violent or more chaotic than we thought. It may be stranger because it is calmer. And calm, when it refuses to break, can be the most unsettling clue of all. Once you allow the possibility that the universe contains structures defined more by constraint than by action, an uncomfortable question appears almost immediately. What else have we been treating as background when it was actually doing the organizing? Cosmology is full of things that feel passive: coordinate systems, reference frames, background radiation. Expansion itself, often spoken of as if it were a gentle stretching rather than a rule that every distance must obey. Most of the time, these elements are introduced early, then mentally set aside, so attention can be focused on the interesting parts: galaxies, explosions, collisions, motion. But once stability becomes suspicious, that hierarchy collapses, because a stable structure is not empty, it is selective. It permits certain histories and forbids others. It does not push events forward, but it fences them in. And fences, while quiet, determine paths far more reliably than forces do. Think about a valley. You can throw a stone into it from countless angles, with different speeds, different spins. The stone's motion feels free, chaotic even. But every path, no matter how wild, is shaped by the same unseen slopes. The valley does not move, it does not react, yet it dictates what is possible. No stone ever escapes upward, unless energy is added from outside the system. Now imagine realizing that what you thought were stones are actually entire histories of the universe. That shift changes how you read almost every observation. Redshift, for instance, stops being just a measurement of motion. It becomes a clue about what kinds of motion are allowed to persist. Large-scale uniformity stops being a coincidence or a consequence of early chaos smoothing out. It starts to look like a boundary condition that never stopped applying. This reframing does not contradict existing data. That is what makes it dangerous. It fits too well. When models assume instability, they often introduce mechanisms to explain why things haven't fallen apart yet. Inflation smooths, dark components balance, feedback regulates. Each mechanism works, mathematically and observationally, but stacked together, they begin to resemble scaffolding built to support an assumption rather than a structure demanded by nature. The strange thing is not that these models exist. It is that they rarely ask whether the instability they are correcting for was ever necessary. If the universe contains large-scale features that are not evolving toward something else, then time itself plays a different role. Not everything is on a trajectory. Some things simply are. And that idea quietly undermines one of the deepest habits in physics, the belief that understanding means predicting change. In this view, understanding might instead mean recognizing invariance. Consider how often the most powerful insights in science come from identifying what does not change. Conservation laws, symmetries, constants. These are not dynamic actors. They are constraints, and yet they shape every interaction more strongly than any individual force. So why should cosmology be different? The hesitation comes from scale. It is one thing to accept a conserved quantity in a laboratory system. It is another to accept that the universe itself might be structured around something that does not evolve, decay, or resolve. That feels final, and finality makes people uneasy. If there is a stable cosmic structure, then some questions lose their urgency, not because they are answered, but because they were misframed. Asking how something formed may matter less than asking why it is permitted to exist at all. This is where the implications become philosophical, without becoming vague, because a boundary is not a thing you can point to. It does not glow. It does not emit. You infer it by noticing patterns that refuse to vary, by absences that persist across time, scale, and method, by the same calm appearing no matter how violently you zoom in or out. And that inference changes how you interpret discovery itself. Instead of hunting for ever more exotic particles or singular events, attention shifts to coherence, to relationships that hold across contexts, to regularities that survive when everything else is stripped away. This is not a rejection of drama in the universe. Explosions still happen, stars still die, galaxies still collide. But these events start to look like surface turbulence, rather than the drivers of the system. The driver is the basin, and once you see the basin, you cannot stop seeing it. The implications ripple outward into how limits are understood, the speed at which information travels, the horizons beyond which causality fails, the fact that now is not shared across the cosmos. These have traditionally been taught as consequences of motion and relativity, but they can also be read as signatures of constraint. Not things that happen because objects move fast, but things that must be true if the universe is organized around certain invariants. The speed limit is not imposed after the fact. It is baked into the geometry of what is allowed. From this angle, the strangest thing we found in space is not a particle or a signal. It is the realization that the universe may be less like a story unfolding and more like a structure being explored. Stories progress, structures endure, and endurance is harder to explain because it leaves no footprints. This is where discomfort deepens again, because if stability is fundamental, then our observational role changes. We are not watching the universe evolve toward something. We are sampling different regions of a configuration that already exists in full. That idea brushes dangerously close to concepts people instinctively resist. Block universes, frozen time, pre-existing frameworks. Not because they are disproven, but because they feel emotionally alien. They do not flatter human intuition about agency and becoming. Yet physics has never promised comfort. What it promises at best is coherence. And coherence sometimes means accepting that the universe does not care about narrative pacing, that some of its most important features do not announce themselves through events, but through the quiet refusal to behave otherwise. At this point in the journey, we are still not naming the thing. We are circling it from the outside, noticing how many explanations bend around it without touching it directly. That circling is intentional, because once you name it, you risk shrinking it, turning a boundary into an object, turning a condition into a cause. And the universe has a long history of punishing that mistake. So for now, it remains what it has always been, a shape you only notice when you stop expecting it to move. And that raises a deeper problem, one we have not faced yet. If this structure has always been there, then there was never a moment when the universe decided to obey it. Which means the real mystery is not how it formed. It is why anything else was ever allowed to happen inside it at all. And that is where things get even stranger. Before telescopes reached this level of sensitivity, astronomers were trained to expect noise before meaning. Most strange signals dissolve with time, a calibration error, a background source misidentified, an assumption quietly corrected in a follow-up paper that almost no one reads. So when this anomaly refused to fade, the first response was not excitement, but irritation. It sat there stubbornly consistent, refusing to behave like an error while also refusing to behave like anything familiar. The discomfort came not from what it was doing, but from what it was not doing. It was not changing in the way models quietly assume everything eventually must. There is a particular kind of frustration that only appears when data behaves too well. When repeated observations tighten uncertainty instead of dissolving it, Scientists don't relax. They grow suspicious, because nature, at scale, is messy. Systems wobble, environments interfere, signals drift. And yet here was something that remained coherent across instruments, wavelengths and time frames. Not dramatic enough to make headlines immediately, but persistent enough to survive scrutiny. The longer it stayed, the more it began to feel like a boundary masquerading as an object. At this point, the human element was impossible to ignore. Teams disagreed quietly, not in press releases, but in footnotes and conference-side conversations. One group framed it as an extreme example of a known class. Another treated it as a statistical outlier that would eventually collapse into the noise with more data. Day third took the riskier path, suggesting that the problem might not be the observation, but the expectation layered onto it. These disagreements were not ideological. They were instinctive. Each reflected a different tolerance for unsettling implications. Because if this thing was real, not as an object but as a behavior, then it implied a kind of cosmic patience that physics rarely talks about. A feature that does not rush toward equilibrium. A configuration that does not decay on convenient timescales. Something that sits inside the universe without participating in its drama. And that is deeply unintuitive, because almost everything we study earns attention by changing. Stars shine by burning, galaxies evolve by colliding, even black holes announce themselves through interaction. Silence, by contrast, is usually dismissed as absence. But this was not absent. It was presence without spectacle. The unsettling realization crept in slowly. What if the universe contains features whose primary role is not to act, but to limit? Not causes, but conditions. Not engines, but rails. Physics is comfortable with forces. It is less comfortable with permissions. Yet permissions decide outcomes long before forces ever apply. You can push as hard as you want against a locked door. The important fact is not the strength of your push, but the existence of the door. This reframing quietly shifts how you interpret countless observations. Large-scale uniformity stops looking like an accident of early chaos. The cosmic horizon stops looking like a technical inconvenience. Even the smoothness of expansion begins to feel less like a process and more like a rule being followed, not enforced dynamically, but respected universally. The universe does not fight these constraints. It never tries to violate them, which suggests they were never optional. Here, another human tension emerges. If the deepest structures of reality are constraints rather than mechanisms, then prediction changes character. You are no longer forecasting motion so much as mapping possibility. The job becomes identifying which paths are allowed long before asking which ones will be taken. That shift is subtle, but it is psychologically disruptive. It removes the comfort of imagining that everything important happens because something did something else. Instead, some things happen because nothing could happen differently. This is where resistance often hardens, not because the idea is unscientific, but because it feels inert. It lacks narrative drama. There is no explosion that creates the boundary, no hero equation that solves it. It simply exists, inferred from consistency rather than spectacle. And yet history shows that the most powerful ideas often arrive this way. Conservation laws did not announce themselves with fireworks. They revealed themselves through what never changed when everything else did. The same pattern seems to be repeating here, but at a scale that makes people uneasy. Because accepting this interpretation means accepting that some of the universe's most important features were never discovered in the usual sense. They were always there, shaping outcomes silently, while attention was focused elsewhere. The strangest thing we found in space, then, is not new. It is newly noticed. And that distinction matters more than it first appears. It also raises a question that no one is eager to answer yet. If this structure does not evolve, does not decay, and does not resolve into something else, then what does before even mean in relation to it? Not before in time, but before in explanation. What does it mean to explain something that never began? Physics has tools for origins. It has fewer tools for eternals that do not behave like constants, but act like scaffolding. At this stage, the temptation is to name it, classify it, pin it down with terminology. But doing so too early risks shrinking the problem, turning a boundary into a box, turning a condition into a cause. And once that happens, the deeper implications slip away unnoticed, buried under language that feels precise but explains very little. So instead, the focus remains on behavior, on patterns that refuse to dissolve, on the calm persistence of something that does not announce itself yet, cannot be ignored. The kind of presence you only notice once you stop expecting motion. Once you accept that not everything meaningful in the universe announces itself by changing. And this is still not the core of the mystery, because recognizing a constraint is only the first step. The harder question comes next. If this structure defines what is allowed, why does the universe explore the allowed space the way it does? Why this richness instead of emptiness? Why motion instead of stasis? Why complexity inside a framework that seems so rigid? Those questions do not threaten the idea. They deepen it, and they point toward something even more unsettling. The possibility that what we call cosmic history is less about creation and more about navigation. Not a story of things coming into being, but of possibilities being traced out over time. Slowly, patiently, without urgency. We are not ready to say that out loud yet. But we are getting closer, and the closer we get, the more it becomes clear that the strangest thing we found in space is not hiding in the darkness. It is hiding in the rules that never needed darkness to exist. At the beginning, this all looked like a detail, a measurement, a curiosity buried inside charts and quiet observations. Something that didn't move the way it should, didn't evolve the way intuition expects. And for a long time, it was tempting to believe that the strangeness lived in the data itself, that with better instruments, more time, or a clever correction, it would dissolve back into something ordinary. That expectation is comfortable. It preserves the idea that the universe is mostly familiar, with only occasional surprises waiting to be cleaned up. But what emerged instead was something far more unsettling. Not an object misbehaving, not a phenomenon breaking rules, but a reminder that some of the most important features of reality are not events at all. They are conditions. They don't announce themselves through explosions or motion. They reveal themselves through restraint, through consistency, through the quiet refusal to change, even when everything around them does. This reframes what discovery really means. We tend to imagine discovery as finding something new, a new particle, a new signal, a new source of light in the darkness. But sometimes discovery is recognizing what has been shaping outcomes the entire time, without ever drawing attention to itself. The strangest thing we found in space was not hiding far away. It was embedded in the rules that space itself seems unwilling to violate. Once you see it this way, other pieces fall into place with uncomfortable clarity. The universe's large-scale smoothness stops feeling accidental. The limits on speed, information, and causality stop feeling like technical inconveniences. They begin to look like structural features, boundaries that were never crossed because they were never meant to be, not enforced by force, but respected universally, without exception. And that realization quietly shifts the human perspective. It suggests that much of what we experience as cosmic drama, stars igniting, galaxies colliding, time unfolding, is happening inside a framework that does not negotiate, a framework that allows richness, motion, and complexity, but only within certain corridors of possibility. The universe is free to explore, but only within lines that were drawn long before exploration began. This does not make reality smaller. It makes it more precise, more deliberate, more strange in a way that does not shout for attention, but lingers long after the noise fades. It suggests that understanding the universe is not just about watching things happen, but about learning what cannot happen, and why those absences matter as much as any presence. And perhaps that is the quiet takeaway. Not that space is full of bizarre objects waiting to shock us, but that the deepest strangeness lies in the calm, invisible architecture that holds everything together. The things that never rush, never decay, never announce themselves. The things that make all other stories possible without ever becoming the story themselves. If you think about it that way, the universe feels less like a sequence of explosions and more like a carefully constrained journey through possibility. Not chaotic, not random, not fully understood, but profoundly shaped by rules that do not care whether we notice them or not. And that may be the most unsettling idea of all. Because once you recognize it, you realize the strangest thing we found in space was never something we discovered. It was something we finally learned how to see. Thank you for staying here, for thinking through this with me, and for giving this time and attention. If you'd like to support these late-night journeys into strange ideas, you can like the video, subscribe to the channel, and leave a comment telling me where you're watching from and what time it is there. Those small signals help others find their way here too. And now, as this thought settles, you can let it rest, not with a bang, but with the quiet certainty that some of the most powerful truths in the universe do not move at all.